Welcome, dear doctor. In this video, we will discuss our project, Traffic Light Controller. First, we have an important question. How traffic lights works. Introduction. This diagram represents a traffic light control system based on digital sequential logic. A clock signal provides timing pulses that control when the system changes states. The digital logic sequential controller processes these clock signals and controls the sequence of traffic lights. The system operates in three main states. Green state, go, allow vehicles to move. Yellow state, wait, warns the signals is about to change. Red state, stop vehicles. The control changes from one state to another in fixed sequence. Green to yellow to red to green, based on clock timing. Traffic light systems are simple examples of sequential logic applications. In this project, a one-way traffic light controller is designed using digital logic concepts. The system operates through three states, green, yellow, and red. A clock signal controls the transition between these states. One-way traffic light controller. To design a sequential one-way traffic light controller, we need 6 things. Sequential one-way traffic light controller includes 1. State assignment. 2. Transition table. 3. Truth table. 4. K-map simplification. 5. Next state equation. 6. Output logic by D flip-flops. State assignment. States are encoded using 2 bits. Green is 00, yellow is 01, red is 10, unused is 11. This slide shows the state diagram of traffic light control system. The arrows indicate the state transition, which occur sequentially based on the clock signal. The system moves from green 00 to yellow 01, then to red 10, and finally returns to green 00.
This slide shows the state transition table of the traffic light controller. Q1 and Q0 represent the current state, while D1 and D0 define the next state. Using this table, the system moves from green to yellow, then to red, and finally back to green, forming a continuous cycle. The output columns show that only on light is on in each state. This slide shows the truth table for the D flip-flops. For D flip-flops, the next state always follows the D input at the clock edge. So, D1 and D0 are chosen directly from the required next state. It ensures correct operation of the traffic light sequence. In this slide, we use K-map to make the next state equation simpler. We draw on K-map for D1 and another on for D0. By grouping the ons together, we get simpler equation that need 4 logic gates. From the K-map simplification, the final next state equation are obtained. D1 equal Q1 dash and Q0, and D0 equal Q1 dash and Q0 dash. This equation controls how the system transition between states. This slide shows the output equation for the traffic light. The green light is active when the state is 00, yellow when the state is 01, and red when the state is 10. This guarantees that only on traffic light is on at any time.
You can see in this diagram that as long as the wire is light, its signal will be 1. So in the green state, the both D flip-flops is sending a 0 signal. With the green AND gate having 2 input bar, the green light will run. In the yellow state, the first flip-flop is sending a 0 bit, while the second is sending 1. So in the circuit, it's sending 0, 1 signal. To make it equal 1 with an AND gate, we need NOT for the first flip-flop, which is the same AND gate for yellow, so the yellow light will run. With the final state, or red state, the first flip-flop output will be 1, and the second one will be 0. Our circuit now have 1, 0 output. We can see that the gate of the red light having the first output in the same and not to the second output. Since we have 0 in the second, it will be 1 and the red light will run. Let's just trace the wiring on green light state. The D flip-flop, the first D flip-flop having a 0 input while sending a zero output to the three AND gates. The second D flip-flop is sending the same output of the first one, which is 0, to the all three. The first AND and the second AND have only one NOT and the other one is pure on both ANDs, except the last AND, which is for the green light, having two NOT for the both output of the both D flip-flops. So it will be 1 and 1 into the AND gate, and output is 1 to the green light. While we run the simulate, we will see the sequence. Also, we will see the sequence. Yes, we will see the sequence running. So in the yellow state, the third output will run and send one signal to AND, and the second one is 0, which is with NOT will be 1, and the output will be 1 to the yellow, while the green having 0 from the first D flip-flop, and with NOT it will be 1, while the second flip-flop will be 1, and with NOT will be 0. Into AND gate will be 0, and the green light will be off. It's the same on the red light. We'll have the pure line with the first D flip-flop, which is the output will be 0 directly, and the red light will be off. So when we run again to the red state, we will see that the first D flip-flop will be 1, and the second D flip-flop will be 0. The pure 0 going to the middle AND, which is for yellow light, and will be 0 output. While also the first D flip-flop will be 0, because the AND and the NOT gate will make the signal 0. So except the first one, which is for red gate, will have the pure line from the first D flip-flop on in this line will be 1, and the second D flip-flop will be 0. Into AND gate will be 1, and the red light will be run. Why there is no state that both flip-flops sending 1? Simply it's because that D1 and D0, which is the inputs of the flip-flops, will never be equal. We can see that the input of the first flip-flop is equal the output of the first flip-flop in NOT, joining the pure output of the second flip-flop to AND gate, while the second flip-flop is having AND gate with NOT for the both of the flip-flop outputs. In conclusion, the traffic lights controller was designed and simulated successfully, and the system cycled correctly through all states. The project helped us to understand how sequential logic, flip-flops, and finite state machine works together in real application. with best triggered. This project has presented by Hatem Ali Asiri, Talal Ahmed Alqsadi, and Mohammed Ali AlShahrani.